All right. So, the very most basic rational function that you will see is f of x equals 1 over x. This is a rational function because it has a variable in the denominator, right? So, it looks like this right here. And it has the dotted lines that I have on this graph are not part of the graph. Those are our asymptotes for the graph. And we've talked about asymptotes some already because our exponential and our natural log functions had asymptotes, right? So a rational function is going to have vertical and horizontal asymptotes, okay? So this function right here has a horizontal asymptote at, get my pen back here, at y equals 0. Okay. Horizontal lines are y equals a number. And that we also could call that the x-axis. Remember, it's back. Your equations are opposite of your axes. So the equation is y equals 0. It is the x-axis. And it will have a vertical asymptote at x equals 0. That would be your y-axis. Okay, so we're going to look at a couple different ways of finding those asymptotes, but you can always plug these into Desmos as well. And I'm going to cut the focus here. There. So, if we look at these problems, this is not our basic. This is not our basic one, right? So let's type these into Desmos and see what they look like. So over here, I'm just typing in example 1, f of x equals 3x minus 2 over x plus 1, x minus 2. Let's make that full screen so you guys can see it. All right. Where do I have vertical asymptotes? Okay. So I'm gonna type in x equals 3. Is that a vertical asymptote? No. Try 2 instead. I think that works. That looks like a vertical asymptote. You can see like it's going to look like you're touching the line, but if you zoom in, it's just getting closer and closer. So I think x equals 2 is an asymptote there. What do you think? There's another one. What do you think it might be? -1. Let's try it. Yep, I think that looks right. Okay? So x equals 2 and x equals -1. We can find those from the graph. Now, let's look at the equation. So we have vertical asymptotes at x equals -1 and x equals 2. Now, look at the equation. What do you notice about the equation that is related to those vertical asymptotes? It's the numbers that would make that denominator 0, right? It's your excluded values, right, that we've been doing for these problems. So when we've been doing excluded values all along, that is where we're going to talk about it a little bit more. In this case, they're vertical asymptotes. They can be holes in the graph. We'll talk about that in a minute. But it's going to give you what we call discontinuity in the graph. So it comes from the denominator. Now, this might also have a horizontal asymptote. So let's look at that. So if you look out towards the ends, is there a value that you're getting closer and closer and closer to? It's not infinity. You're approaching infinity. What are the y values doing? 0? And if it's a horizontal line, what's the equation of a horizontal line? Y equals 0. Let's graph that. And so it does like cross it here in the middle, which makes you think maybe it's not it. But that can happen. What you're just looking at is at the ends, does it look like asymptote? And if you look over here, like it looks like they touch, but if you zoom in, they're not actually touching. So we have a horizontal asymptote at y equals 0. Okay? You guys try 2 on your own. Look at 2 on your own. So type 2 into Desmos. This one's kind of weird, isn't it?
Oh, I did. So Miss I is not your favorite teacher? Okay. I never said Miss I.
Okay, this one's weird. There's one I think you should be able to come up with fairly easily. Maybe 2. All right, give me a vertical asymptote. What is it? 1? X equals 1. Does that look like a vertical asymptote? I believe so. That looks, I think, good. Oh, gracious, what have I done? Okay. I think that one looks good. All right, anybody else know another asymptote? X equals 2. Okay, it looks good here. If I zoom out, it crosses. It's not 2. Okay, let's try that. Okay, let's see about that. Click on it. I think that looks better. I think it is 1.5. All right. What about a horizontal asymptote? Y equals 0. All right. So when you're thinking about horizontal asymptotes, you're only thinking about the ends of the graph. So it might cross it in the middle, right? And you can see it crosses here. It's okay. You're thinking about on the ends what is happening. Does that look like an asymptote on that left side? It does. If you click on it, they don't cross. If you zoom in, they are not touching still, right? And then on the right side, you can see you're looking at the ends. Same thing. They don't cross. If you zoom in, they're not actually touching. So, for this one, we should have vertical asymptotes at x equals 1 and x equals 1.5. And then a horizontal asymptote at y equals 0. Okay? Now, let's talk about how to get 1.5 from the equation instead of the graph, because that one was hard to find, right? Most of you got 1, you did not get 1.5. How do I find that one from the equation? Right, you're looking for what gives you a 0 in that denominator. So 2x minus 3 equals 0. You would add that 3 to the other side. 2x equals 3. You divide by 2, and then x equals 3/2, or that is 1.5 for that. So you set that factor equal to 0 and solve. It's not just the opposite sign whenever you have a number right here. Okay, questions? All right. Okay, so there are two different types of discontinuities that you can have in rational functions. You can have removable discontinuities, which are also called holes sometimes, and removable discontinuities are called this because they could be removed with just one single point. Okay, so if you look over here at this graph, you have a removable discontinuity right here at this point, and it'll be shown by open circle. Okay, so it's just one point on the graph that's missing. Right? We call them holes. It's pretty obvious, I think, why we call them holes in the graph right there. The phrase you might be more likely to see, though, like on the EOC, is removable discontinuities. They might use the word hole, but they might call it a removable discontinuity instead. Okay. The other type that you will see on a rational function is a vertical asymptote, and that would be, in this particular case, it is right here. We got that line that we get closer and closer and closer to for that. So for this graph, we would say that we have a hole at x equals, what's the x coordinate where that hole is at? Are you sure it's 2? -2. And we have a vertical asymptote at, what's our x value there? -3. Now, these are called discontinuities of the graph, because if you were tracing this graph with your pencil, you have to pick up your pencil. The graph is not connected from here jumping up to here, right? So a discontinuity means it's not continuous. It's anywhere you'd have to pick up your pencil. If you were tracing here, you would technically have to like pick up your pencil, jump over that hole, and keep going, right? All right, questions?
What if there's a line in between the two graphs?
Like the other ones we looked at where there were like more than one. You can have more than one. Yeah, you can have more than one vertical asymptote. This one just has one, but you can have more than one. Okay. Okay, so one of the problems we are going to run into is that a lot of this can be done from Desmos, and I encourage you to use Desmos to help you, but not all of it. When you graph this graph right here on Desmos, this is what the graph will look like. The issue is holes do not show up on Desmos. In fact, let's graph it right here on a live graph so we can see. F of x equals x minus 3, x minus 7, x plus 2, x minus 3. Okay? All right, so on this graph, where do I have a vertical asymptote? It's somewhere right here, right? What do you guys think? X equals what? Negative 3? I don't think that's it. I think it's too far over. Let's try negative 2. Negative 2. I think that's it. Let's sort of zoom out a little bit here. Oh, yeah. I think x equals negative 2 is our vertical asymptote. And I can see that right there. It should be at negative 2, right? But what about x equals positive 3? Right? That is also in the bottom. But do I have a vertical asymptote at x equals positive 3? I do not. Okay? In fact, what's happening at 3 is almost impossible to see on the Desmos graph. Okay? What's happening at 3 is you have a hole in the graph. So if I get, oh, there it was. Let me zoom in a little bit more. All right. If I go to where x equals 3, which is right here, and it's really hard to find on Desmos. If I can get right to that point, if I'm clicking on that graph and get right to that point, it'll tell me it's 3 undefined, and notice how it makes it an open circle. But it doesn't graph it like that automatically. That is because points are, like, if I can go to, like, 2.9999, the value still exists, right? So whenever you graph it, it doesn't really show up on there. But if you go straight to that point, it will show up. But that makes it really hard to find from a graph, because if you're just like going along the graph trying to find that point, like I just went right over it. Oh, I did see it there, but like you can go right over it and not see it, right? So, so we need a better way to find holes in the graph than just looking at the graph. Vertical asymptotes you can pretty much find from the graph all the time, but holes are difficult to find. So let's talk about what causes a hole, okay? Vertical asymptotes are going to occur at values that make only the denominator equal to 0. Removable discontinuities, or holes, occur at values that make both the numerator and the denominator 0. So, anytime we're looking at discontinuities, we really mostly only care about the bottom, right? So, if I see this, I would know that I would have a discontinuity at both x equals negative 2 and x equals 3, because I have something in the bottom that would give me a 0. But only one of them is a vertical asymptote. The other is a hole. Okay? If you have a vertical asymptote, then this value does not cancel out if you're like simplifying it, right? But if I look right here at this x minus 3, what happens with the other x minus 3 up here in the top? If I was simplifying this, those would cancel, right? So another way we could think about this right here is a 0 in the denominator that cancels with the top. So when I see that the x minus 3 and the x minus 3 will cancel out, that tells me this one is a whole. The x plus 2 does not cancel out, so that tells me this one's a vertical asymptote. And I'm just using VA for vertical asymptote there. Okay, so it's going to be important that we know how to do this with the equation, because it's going to be hard to do it with the graph for the whole part of it. Okay, questions? All right, moving on. Okay, for each function, we are going to find the x value for all discontinuities and describe the type of discontinuity at each value. Okay, so what I would like for us to do is I want us to do it by hand, and I want us to check it using Desmos. Okay, because it's good to know both things. So anytime you're doing discontinuities, you are looking at the bottom of the fraction, because the bottom cannot be 0, right? That's why we've been doing excluded values this whole time. The bottom cannot equal 0. So in this particular case, what value would make that denominator 0? Is it positive 5? It is not, because we have a number in front of our x, right? So we're going to say, we're going to say 2x minus 5 equals 0. So we have to add the 5. So 2x equals 5. We divide by 2. Okay? And so x would equal 5 halves, or if you want to do 2.5, that would be the same. Okay? That is definitely a discontinuity. Is it a whole or a vertical asymptote? It is a vertical asymptote because it doesn't cancel with the top because there's nothing in the top but a 1, right? So it doesn't cancel. Okay, so discontinuities are pretty much the excluded values that we've been doing all along, right? And now we're just having to tell what type of excluded value it is. So if I look, oh, let's check that on Desmos. Let's see. See, you can check this on Desmos by typing in your equation, y equals 1 over 2x minus 5, and let me pass the button right there, and then type in x equals 5 halves and see if it looks like a vertical asymptote, and that does, so that should confirm what we were looking for. There. Okay, questions on that? Okay, so again, we're looking at the denominator. Think excluded values. So, Victor, if I look at 5x times x minus 4, what are my excluded values? What values will give me 0 in that denominator? Okay, 4, because if I put a 4 right here, I would have 4 minus 4, that'd be 0, right? So we're going to definitely have a discontinuity at x equals 4. All right, there's another one. What is it? It is not negative 5.
0.
It is 0. Because what we're doing for this is we're taking 5x and we're saying that it cannot, or in this case, not that it cannot equal 0, but it does equal 0 because it's asking us for the discontinuity. Divide by 5 is how you solve that, which just still gives you 0. And the other one, you're doing the same thing. We just have not been writing it for that because you're doing x minus 5 equals 0. And then if you add the 4, x equals 4. Okay, now, I need to decide what, these are both discontinuities. Right, these are both discontinuities. Both of them are discontinuities. And then I got to be able to tell what kind of discontinuity. So, what causes a whole? If it cancels, okay? Does anything cancel here? What cancels? No. Look at the equation. Think about simplifying. If I'm simplifying that, is there anything I can mark out? Anything I can cancel? The x's can cancel. Because this x right here can cancel with this x right here. Which one did that go with? The 0 or the 4? It went with a 0. So that means this one is your whole. Or your removable discontinuity. Right? Does the x minus 4 cancel? It does not. So what do I have here? Vertical asymptote. So if it cancels, it's a whole. If it does not cancel, it's a vertical asymptote. Okay, let's check it on Desmos and see. I've got y equals 2x over 5x times x minus 4. And if I look at that, if I've got x equals 4, that definitely looks like a vertical asymptote right there. At 0, if I can, oh look, I got first try right there. If I click at 0 right here, it says undefined, there is a hole. It's a little easier to tell on the graph if you already know where it's supposed to be, because you can just point there and click. If I've got to go like this, it makes it pretty hard. Like I did see it right there, but just for a split second, right? So if you know where it's supposed to be, it makes it a little easier to find. Okay, questions? All right, what in the world are we going to do for number 5? What would make the bottom of that 0? Oh gosh. You've just killed it. You've just killed the math fairies. We need all the math fairies we can get. Can I mark out that minus 4 and minus 4?
Yes.
I cannot. I cannot. Because that 4 is separated by a minus sign, right? I cannot do that. Because it's separated by, like, the minus sign right there. Well, you can't do it because it's not multiplied. It's not multiplied by those numbers. We can only cancel things if they're multiplied. Do I have anything that's even really multiplied right now? No. What can I do to the bottom? Everybody's favorite. Factoring. We love it. So much fun. Negative 4 is what we're trying to multiply to get. Negative 3 is what we're trying to add to get. Okay? I have an x here. X here, what works? Negative 4, positive 1. So negative 4, positive 1. Does that work? Right? Okay, so now when I have it factored, can I tell what my discontinuities are going to be now? Oh. X equals positive 4 and x equals negative 1. They are both discontinuities. But do I have a hole in the graph? Will anything cancel? The x minus 4s cancel. So when I have it cancel, what does it tell me?
There's a discontinuity there.
What kind?
Hole.
A hole. Right? So I've got a hole whenever it cancels. But over here, does my x plus 1 cancel? No, so what do I have there? What does V point A stand for? Vertical asymptote. All right. Okay. Y'all try that. Y'all try that last one. Try that last one. See what you can do with it. It's not too hard. Now, there's only one discontinuity, but what are you going to have to do to tell if it's a whole or a vertical asymptote? You got to see if it cancels. Does it cancel right now? No, but what have you got to do to that top? Everybody's favorite. Factoring. All right, everybody try it.
More done, Angel.
All right. All right.
3 and 2. Oh, it's a whole.
X plus 3x plus 2.
No, X minus 3. Yeah.
Okay? Now, when we're looking for discontinuities, we only look at the bottom. The only reason we're factoring that top part is to tell if it's a whole or vertical asymptote. So, we only have a discontinuity at x equals 3. What type is it?
A whole.
It is a whole, because x minus 3 will cancel with this x minus 3 here. Do I have anything at x equals 2? I don't have a discontinuity. It's a 0 of the function. It's where the crosses the x-axis, but that's not what they're asking us for here. So no discontinuities. The top is only factored just to see if something's a whole or not. You don't get anything from that. Okay, questions?
So would X minus 2 be the
No, this one doesn't have a vertical asymptote. In fact, if we graph it, let's graph this one because this one's an interesting graph. If we graph it, f of x equals x squared minus 5x plus 6 over x minus 3. What does it look like when we graph it? It looks like it's just a line. But if we go to where x equals 3, right here, oh, there it was, it's got a hole in the graph. So it's a line, but it's got a hole in the graph. And that is why it's really helpful to know how to do this by hand, because it's not always easy from the graph. All right, got a couple more slides, and we'll be done with this part. Okay? All right, so given this graph, I want to find all x values for the discontinuities and describe the type of discontinuity. So sometimes you do it from a graph, you don't even have the equation. All right, so do we have any holes? All right, where? I need you to be more specific. Okay, at x equals -5. We're given the x value where it happens, not the y value. So you're given the x value where it happens. Okay? All right, is that my only hole? I think so. All right, and if it's a graph, they will show you it is a hole with an open circle. If it's a, they won't give you this and expect you to know there's a hole somewhere that they haven't shown you. If it's just the graph, if they give you the equation, they might. But if there's no equation, it'll be shown. All right. How many vertical asymptotes does this one have? It's got 2. So vertical asymptotes at where? Okay, -2 is right here. I think that looks good. And +3 is right here. I think that looks good as well. So we would say x equals -2 and x equals +3. Okay, everybody good here? Might should move that one up in the notes on. It's not too bad. All right. Okay, now, what do these ask us for?
Domain and range.
Domain and range. Okay, we have done domain and range quite a bit, right? We've done them for several different types of functions. Domain are my x values. Range is my y values. Okay? And so we've done these for lots and lots and lots of problems. For rational functions, your domain is going to be basically everywhere except for your excluded values, your discontinuities. Okay? So it's very similar to what we've already done, but just a little bit different. Let's graph this real quick. So if I graph f of x equals 1 over x minus 5. All right, this is the graph that I get. And so if I do x equals like 1, it will put, no, x equals a. Will it not let me do a slider for that? Okay, there we go. We got a slider. Okay, so if I like go back and forth, my line hits the graph everywhere that I'm looking at, except where? 5. So this graph exists everywhere except for your discontinuities. Okay? So there are two ways you can write this for your domain. For your domain, you can say all real numbers except x equals 5. So everywhere except x equals 5. Or you can use interval notation. It would go from negative infinity up to 5, but with the parentheses because you're not including 5, and then from 5 to infinity. We have to know both because they may use either one of those on the exam. Like your answer choices might be either one there. Okay? Now, range is going to be our y values, and these usually have a restriction on the y values because there's going to be a spot where you can't have a y value. So let's look at the graph for this. We're mostly going to do these from the graph. If I change this to a y, it'll put me a horizontal line, and then I can use my slider right here. Where do I not touch the graph? It was right there at 0, right? I have a horizontal asymptote at y equals 0. So that means my graph never actually equals 0 on that y-axis. So over here, I could say, is that all right with you guys if I use this symbol right here for all real numbers? That R with the double bar means all real numbers. So all real numbers except y equals 0. If you do it that way, make sure you put a y because it's for this is your y coordinates. Or they might do it this way: negative infinity up to 0 and 0 to infinity. Make sure you're using parentheses so that 0 is not included. Okay, let's look at example 9. Okay, for example 9, whenever we are thinking about domain, we're thinking about the discontinuities, the denominator equaling 0. What type of what are going to be our discontinuities here? So discontinuities, x equals 3 and x equals negative 2. It does not matter if that is a whole or a vertical asymptote. They're still discontinuities. So x cannot equal those values. So your domain would be all real numbers except x equals 3 and x equals negative 2. Or if they use interval notation, here's how it's going to look. I don't love doing interval notation on these because it's harder. You got to go from negative infinity up to, if I start at negative infinity, which discontinuity am I going to come to first? 3 or negative 2? Negative 2. And then I would go from negative 2 up to the next discontinuity, which is 3. And then I would go from 3 up to infinity. Okay, now, which one of them is the whole? The negative 2 is the whole. The 3 is the vertical asymptote. But if it's asking for domain, it doesn't matter which one's which. Okay? All right, let's look at our graph on that one for our range. So we've got y equals x plus 2, x minus 3, x plus 2. All right, and I can, if I do y equals a number, not capital Y, it'll put a slider here. So there's going to be a lot of times one that's really hard to see here. There's one that is pretty easy to see. Where does this graph not touch? 0, right? I have a vertical asymptote, a horizontal asymptote at 0. But at 2, or negative 2, I've got a hole in the graph, right? So, right here, if I click on that red graph, at negative 2, I have another hole there, right? So, do I have to tell you how to find that? Gosh, that's practically calculus. I don't think I have to tell you how to find that. But I need to for you to answer this question. Okay. It's not that bad. It's not that bad how to find it. Okay. So, 0 you can see from the graph. So it's y equals 0. To find the value for the other one where you have a hole, here's what you're going to do. You're going to go ahead and simplify it. You're going to cancel. So you'll cancel that. And since there's nothing left in the top, there would be a 1. And then you're going to plug in the number for the hole. I'm probably not going to give you one where you got to do this. But if you plug in the number from the hole, that would be 1 over negative 2 minus 3. And so it is going to be y equals negative 1/5. So the range on this one would be all real numbers except y equals negative 1/5 and y equals 0. Or it could be written like this, negative infinity up to negative 1/5, negative 1/5 to 0, and 0 to infinity. Don't worry too much about that. Finding that negative 1/5, it's not going to be the end of the world. Okay, you guys try domain and range on 10 and 11 for me. And we'll come back together to see what we get. Yes, you will need to factor on number 10. Are you asking how I got to infinity? How do you draw it? Sideways 8? Or you take it sideways and draw an 8? Right, good. You're actually, this will be the 2 on top and 3 on bottom. The last number goes on top. And 3 goes on top. Multiply and add. So what number is getting multiplied? Right? And if you add 2, it will give you 30, right? So that'll factor into x plus 2, x plus 2. The top part will be x plus 2, x plus 4. Yeah, so there's a parentheses. And so on the bottom you got x minus 2. Okay. So does anything cancel? So you just have like a vertical asymptote at 2. So that will be like the number it cannot be. Yep.
So after I factored this, I've got x plus 2.
Single cancel. So what type of discontinuity do you have?
I guess this is
Square bracket at 2. So that's going to be the number you cannot equal in your domain.
just one result.
Yep, and there won't be any holes. All right, we're running out of time, so let's go ahead and go through these. So you should factor right here. You will get x plus 2, x plus 1. And does that cancel with the bottom? It does not. So you have a vertical asymptote. So your domain is going to be all real numbers except x equals positive 2, because when we're looking for discontinuities, we're only looking at the bottom, right? Or that might be written negative infinity to 2 and 2 to infinity. And so if we look at the graph of this, we're going to look for our range. All right, and this one's got a slant asymptote. Ooh. All right. We got like a big chunk that we're missing, don't we? All right, so what is the y coordinate here is 0.72. And then you got nothing in the middle until you jump up to here where you got this low point, and it's 13.928. So this one's a little weird. So it's going to be your range is going to be, I'm just going to do interval notation for this. Negative infinity to 0.72. And then, what was that number here? 13.928. To infinity. That one has a slant asymptote, which thankfully we do not have to find in this class. We have to do it in pre-cal, but we don't have to do it here. Okay. Let's do 11, domain. What number can I not have?
2.5.
Not 2.5.
1.5.
You're getting close.
1.5.
Negative 1.5. Okay? Because you're doing 2x plus 3 equals 0. Subtract that 3. 2x equals negative 3. Divide by 2. X equals negative 1.5 or negative 3/2. Okay? That also could be written negative infinity to negative 1.5. And then 1.5 to infinity. And then we want to use Desmos for that range. Y'all quiet back there? Okay. Looks like we have a horizontal asymptote on that. Is it 0 this time? It's not. It crosses at 0. So if I hit enter so I can slide this up. 0.5? Does that look right? Without teaching you something else, I can't tell you exactly how to find that, although I know how. But it is a calculus limit, so we're not going to do that. We're just going to go with the graph. So you can't have 1.5, so your range would be all real numbers except y equals 0.5, or we could do negative infinity to 0.5 and 0.5 to infinity. I can't remember. I have to look and see. I can't remember if we've got a quiz on the end of this unit or not. We're getting close. We just have one more section. All right. So your assignment, you got to go do at least one question. All right. Your assignment is going to look like this. Okay? You have 4 questions that are they're kind of multiple choice. Some of them, like this one, you can include more than one answer. So, like, you could pick these 2 here, and we'll see that. Are they full screen? No. Okay. Then your last ones are matching. Okay, so you got a couple where you got to match the graph to the equation. Okay, you can use Desmos. You can also like use what we've learned to find the zeros and see where you have holes if you would like as well. But either one, just be careful because sometimes it's hard to see the holes. You might need to click on the graph because like this one right here has a hole. It's a little hard to see in that small graph. Okay, so look out for that. Okay? All right. So go answer one question right now. Everybody before. Oh, sorry. If it's not live for you, then you're cheating on something on class-wise. Well,